Life cycle of a star. Our sun right now is an average star and it has a life cycle, and it had a beginning, a birth, and it's kind of going right now. It's still at a young stage of its life. It'll probably go through a midlife crisis and be a red giant, red supergiant, and eventually become a white dwarf. Now, I want to remind you that these different colors give us a hint on the energy of the stars. So remember, red is a lower energy color. So the red giant is more of a lower energy star. And if we look back at some of the things that we've learned just recently from the electromagnetic spectrum, so that light is coming from us because of the excited electrons. And the electrons will be excited because you're fusing them together with lots of energy. And so when you excite the electron jumps up, giving you off a specific color. These different jumps give us the different colors and gives us that spectrum. Now, different elements, here's an example. Again, we'll have different jumps. And we see that color, like neon has several jumps, but we see the neon signs as one color. But what we have is we can use spectroscopes to split those colors, just like a prism splits white light. The spectroscope is going to split all the colors of the light, giving us the many different colors that these elements are giving off. So, for example, carbon is going to give off several colors that we see just as one color, but the spectroscope will split it. And so, as you can see, it has several different jumps. And so, if you look over at carbon, it has that red, the green, and sort of the purple jumps, and even some infrared uh, jumps as well. So, life cycle of a star. The nebula, again, is just kind of a big ball of gas, a bunch of hydrogen, and it starts slamming that hydrogen together to give us a protostar. Now, depending on how much mass that protostar has, will depend on what color of the star will be. So, the mass of a developing star determines the way it will look and the life it will take. So, if you look at lower massive stars, they're red, orange, and yellow. Our sun is a main sequence star. And the cloud of gas will be pulling in due to gravity. And the very size of the stars will have varying colors. Smaller masses can't fuse as fast, and they have less gravity. And so slow fusion means low energy, and thus slower energy electron jumps, and thus the redder color. So low mass means less fusion, and so a lower energy color. If once that star dies, it will implode on itself and expand out those gases to a red giant. That red giant eventually will lose all its gases and just leave behind a white dwarf. Now, if you have a more massive star, these are bigger, bluer colored stars, they will have more mass and so more fusion, higher energy electron jumps, so a bluer color. When they die, they will actually blow up to a supergiant, but they'll have so much mass that they'll be able to pull back that mass into a neutron star, a supernova, or a black hole. And so we're going to be learning about all of that today in your Google form. So the Big Bang was made hydrogen atoms, and that's kind of called the beginning of the Big Bang was called threshold 1, the beginning of it. Next week is the Big Bang, so we'll talk about it all next week. And so in the nebula is just a bunch of hydrogen, and that hydrogen has mass. And anytime there's mass, gravity is going to pull it in and form all that hydrogen is going to come together, giving you a protostar. You can't see it right behind here because a protostar. Electromagnetic force of electrons is useful here on Earth. The negative charges of the electrons repel and protect the nuclei of the hydrogen or any other atom. But an extremely hot protostar, proto meaning the beginning, the electrons get so excited that they are not able to remain connected to the protons of the hydrogen. The electrons are still nearby of the orbiting protons, but they're not able to stay within the orbit. And so then these protons are sort of fused together because, again, they can't repel each other anymore due to the large gravity and the hot temperature and gravity, they start fusing together, making a heavier nucleus, which is considered a new element. So the nuclei of the two hydrogen atoms bash together, stick to form one nucleus, creating fusion reaction, which gives off even more energy. This energy excites other hydrogen atoms, causing them to fuse, giving off more energy, creating a chain reaction. So that fusion gives off energy, which causes more fusion to occur and more energy. This chain reaction of fusion and energy ignites the ball into a main sequence star. So as you can see from the image to the left, the process of actually fusing hydrogen to helium is not as simple as just smashing 4 hydrogens all together. There are some gamma rays given off, goes through several different processes, and even some neutrinos. Now that may be a new symbol to us. A neutrino is very similar to an electron, but it doesn't have a charge. It's one of the most abundant particles in the universe. They have very little interaction with anything because there is no charge and it has such little mass. But some of it is given off, and also some energy is given off because the masses don't quite add up to a helium. But the hydrogen masses don't add up to a helium. So after hydrogen starts slamming together, there's used up, you get helium left over, and those helium start fusing together to give you beryllium. And then elements like carbon and beryllium are now available to fuse into elements like nitrogen, magnesium, and silicon. So there's this whole fusion process going on inside a star we've already done these reactions before. Last week or a couple weeks ago, they're fusing together to make heavier elements. Sometimes just energy is given off. This is all done inside of a star. So the lighter elements are formed, giving off energy. So this is a graph of energy given off by the element's mass. The low gravity of the smaller star is able to push hydrogen nuclei together and fusing all those slightly heavier elements. Note that the more massive the element, the less useful and more difficult it is to fuse. Smaller stars can't fuse elements past silicon really all that well. We're only going to get a couple more elements before we actually need to put energy in order to fuse. And we know, if you know anything about stars, they don't want to put energy in. Energy's all going out. So once we get to this element, and it's going to be iron, there will be a death to the star. So inside the smaller stars, these first lighter elements up to silicon are formed within the sun. So eventually, those elements will be too heavy and the star will implode on itself, forming a red giant, pushing the gases outward. And over time, those gases will float away, leaving behind just a white dwarf. If you can see here, the ring nebula is the remains of a red giant. Somewhere near the center is a white dwarf. So the heavier elements, the more pressure, the heavier the element is, the more pressure that comes from the electrons trying to surround that larger. There's more of an electron shield. So this makes fusing more and more difficult for the star as it collects heavier and heavier elements to the core. Only very massive stars have the gravity to continue fusing. But even these atom factories have their limits. Not only are heavy elements resisting fusion, they are also giving off less and less energy. The life cycle of a star depends on this energy source. So if they're giving off less energy, soon the star will eventually die. And that pretty much happens at iron, because at this point you need to start putting energy in. So the final element will be giving off energy as iron. And this is the sticking point for fusion. So eventually their star becomes so massive with iron, it will implode on itself and die. So large stars can still make the elements 2 through 14, but they're mostly made in the small to medium stars here. As you can see, the turquoise blue here. And the larger stars form up to iron. But that's really not even halfway through the periodic table. And I'm kind of telling you already that the star is going to die here. So there must be some other way that the rest of the periodic table of elements is formed. So at this point, these stars will also die and form a supergiant. However, these are so massive that the gases can't escape. The gases are actually going to remain around. And the lighter stars, the gases escaped and you just were left behind with the white dwarf. But stars larger than a 1.4 solar mass, our sun is a 1 solar mass, expand just like red giants, but strong gravity does not allow those gases to escape. The heavy core of the supergiant won't allow them. So the electromagnetic force of the iron electrons in the core will not be able to withstand the cumulative gravity, and they start to implode on themselves. And forms a supernova. Now imagine all those elements slamming together are going to eventually give you some radioactive elements. There's neutrons in there, there's neutrinos. They're slamming together, and they're going to give you some pretty heavy elements. And that, by the death of the star, will give us the rest of the elements on the periodic table. So let's take an inside look at the star's death. So as you get bigger and bigger, the gases expand away, but the gravity will not let them completely escape. So they're getting bigger and bigger. And then if I look just on the inside of the core where all the iron is so heavy and dense that it will implode on itself. So this is the dense core here, just built up a little bit bigger. So all that gravity iron collapses on itself, leaving sort of a vacuum. Well, if all these are gases out here, you know what those gases are going to do. They're going to fill in that space right there, but they're going to bounce off and ricochet off that dense core that's been formed. But then there's still more gases falling in. So there's gases going in, gassing coming out, and there's going to eventually be a huge shock wave, which we call the supernova. And it's a death to the star. So this creates the huge shock wave, causing massive fusion reactions much greater than the star has ever experienced, creating a supernova. And this will be such a bright light in the universe that it'll be able to be seen in a galaxy, shining brighter than the rest of the galaxy. So there you have it, folks. These are all formed within the sun. And when the star dies, you implode it with all the other elements, forming very radioactive uranium, neptunium, thorium. All these radioactive elements are unstable. And guess what, folks? They're going to decay. They will decay over time, giving most of the rest of the elements. And this is done through your alpha process, beta, and fission decay processes. So you get most of these rest of these elements through the fission process. Up here was fusion in the star, and below is fission. Okay, so here's the big periodic table. If you were able to separate it and put it all in one, if you put the d orbitals, that's what it would look like. So again, up here is fusion, kind of showing you the fusion process is done in the star, and the fission process is done during the death of a star. So obviously, if you look at an abundance of elements, hydrogen and helium will be up there since they were there from the beginning. And the next are the elements that are formed within the smaller stars, then the stars that are formed, the elements that are formed in the heavier stars. And then the rest of the elements are from after the death of a star. Note there is a spike due to iron because that's where from the death of all of it's going to be implode. That's what's mostly being made at the end. And if you see this kind of wick right here, that's because helium is an important building block and it's an even number. So there's a greater abundance of elements with even numbers. So that's why even numbers are a little bit more spiked than the odd numbers. So after a death of a star, there's debris flying all over the place, which a lot of the hydrogen gases and helium gases will come together again. Guess what? Giving you a protostar. But there's all these other elements that will start clumping together to give us our solar system. The heavier elements will stay closer to our new star that's being born, and the gassier elements, lighter elements, will fly further away. Those gassier elements the lighter elements will give us our more gaseous planets, and the more heavier elements start clumping together, forming orbs and spheres, giving us the more dense elements. And guess what's at the center of these core of these elements? It's iron, which was most abundant at the death of a star. So our planets were actually formed from a dying star, and our sun was formed once from another death of a star. And so here we are in our planetary system, the third rock from the sun. And then that solar system is just a tiny dot on the Milky Way galaxy. And so if you think that our solar system was formed from a death of a star, there's got to be other solar systems as well that formed from a death of a star as long as they have water, there will be life on that planet. So here we are in the Milky Way galaxy and feeling pretty small right now, and kind of amazing that we are all made of stardust because it was once eventually a death of a star that made our solar system. I hope you enjoy this. In the next video, you'll see kind of an animation of the cycle of a death of a star, the supernova. And I hope you're enjoying the Google Forms and it's not too tricky for you. Hope